Okay, continuing on with homework number 10, here is problem number 2. I think I forgot to write down 2 right in here. Some of the other things I can write in here. Let me finish this up here. I'll fix this when I get to it. Just fix it when I get to it. All right, so we have, I'm making a slight little joke here. The aerospace people are up in space in the previous problem, but we mechanicals are just playing with boxes on slopes. And we have a large box that's moving down a 15-degree slope that has friction of 0.4, coefficient of friction of 0.4. It's got an initial velocity of 13 feet per second. At a time, 0.896 seconds later, it seems very specific, doesn't it? It collides with the stationary smaller box that weighs 13 pounds, and they stick together and they move as one. When to determine the time after the impact when the two boxes stop. Okay. So, just in full disclosure, in the original problem, I looked at a problem that I liked, and I said, "Oh, this would be a good one." Originally, I think it had distances in it, and I looked at it and I'm like, "Oh, actually, this is like a work energy problem." So by making it time instead. So originally it moved 10 feet. We can go backwards and look at that. If I have time, I'll mention it. So it moves here delta t. I guess I need to remove this thing here. And maybe I'll write on here to try to communicate it here. Collision at delta t, and delta t is equal to 0.896 seconds. We want to find delta t. Maybe this is delta t1, delta t2 to stop. Okay, let me double check my emails because I might have somebody. No, nobody outside my door. All right, so let me double check my nobody in Collaborate either. It's all right. Okay. So one of the first things I'm going to need to do is find the friction force on there. And to find the friction force, we will need to write an FBD and an IBD. So I'll start off with that. So an FBD, even though it's not a Newton's second law, we were told, I think in the problem, let me see, did I say it in the problem? I meant to say it in the problem. In the problem statement, yeah, use impulse and momentum for this problem. There. You could do it with Newton's second law, but we're going to do it this way first. All right, so we'll write out our FBD for the first box. And like I said, I wrote in the problem statement that we could actually solve this problem if we were to find the acceleration. Then we could figure out at a certain time what its velocity is going to be just before it hits that. So that's our main goal, actually, is to find that velocity. So we're going to have this weight that's acting down there. So that's going to be WA. And we're going to do coordinate axes that look like this. All right, so we're going to go x prime, y prime. And IBD should be labeled on top of it, right? That sounds a little better. Okay. And so that's the weight, and here's our angle theta. And here's our FN. In fact, I'm going to call it FNA because this is just box A by itself. And here is my FFA. I did that correctly, yeah. And if we were going to do this, we'll have MA, acceleration of A. Right. Now we're only doing this in the y prime direction. We could find the acceleration of this, but we want to use impulse and momentum. It's just sort of a demonstration of impulse and momentum. In this situation, I probably would go for Newton's second law. But let's just go ahead and proceed. So here's the y prime direction, mass times acceleration in the y prime direction. But we know that's going to be 0. So the whole point of this is to get the FNA. And we have minus WA times the cosine of theta, because it's the adjacent side, right, that we're aligning with the y prime direction, equals 0. So we get FNA is equal to, I don't want to write it out again, it's just 22 pounds, right, 22 pounds cosine of 15 degrees. And I did write this somewhere else right here. So at some point we have to write some numbers down, but I think it's 21.25 pounds. So I want to get the friction at A is going to be mu K times FNA, or 0.40 times 21.25, and we're going to 8.500 is the friction force that we needed. Now we're going to do impulse and momentum. And I like to go imp mom. Let's go impulse and momentum. And so we're going to use 3 diagrams for this, right? So the 3 diagrams are going to look like this. I need to write them. I need to label them for it. I'm going to label them first. I'm going to go initial, impulse, and then final. Although it's not final because we're going to do another thing after it, but that's good enough. All right, so we have this guy right here sliding down the thing, and here's the impulse. Here's the impulse part of it. Okay, so I hope I repeat this statement a bunch of times. I can't recall if I did. A lot of times we have to ask ourselves whether something, the acceleration is going to be constant or not, or if it's going to vary. We don't necessarily have to do it in this instant, but we have to ask ourselves: is the force constant? That's another one, right? And have to when we want to know whether the acceleration is constant, it's best to ask ourselves: is the force constant? Here's another instance where, like, if I want to try to integrate, right? So, like, let me write this out first, okay? So this thing has momentum in that direction, right? So I guess maybe we will go ahead and use the coordinate right here. We'll go, this is still x prime and y prime right there. So we're going to use in the x direction because this is mass of A times velocity A1. Right, that's the momentum thing. We want to say that it's plus, it's going to be equal to it. Here is the impulses that could be acting on it. All right, so we have weight that is acting onto the thing, right? Now it's WA, but it's got to be WA times delta T. And the question is, should I make it an integral? Not if the force is constant. Then it's just force times the change in time, right? We didn't have to do the integration like we did in the last problem. And that's one of the reasons why he did that last problem. Here's another one right here. We go force of the normal times delta T. Like, ask yourself, does that ever change with time? It doesn't. Therefore, we could take, it's just the constant force times time. Here is the friction, and go friction FA delta T. It too does not change with time. And then we can go, this right here will be mass of A times the velocity of A2. And if we're going to write out our main equation here, we'll say L1 plus the imp 1 to 2 as a vector is going to be equal to L, and that's the linear momentum. And then write out the other equation for it. V1 plus integral of F as a vector dt from T1 to T2. equal to the sum of the momentum afterwards. Right. So now we'll go like, here is the x prime direction that we're going to write this all for, because it makes sense to align it in this direction. In that direction, we have the mass A times velocity A1. It's positive because that's what we decided positive was going to be. We're going to have the weight is coming in that direction, so it's positive. So right here times delta t, but that impulse, we're only going to take the sine of theta. Then we're going to have a negative here because it's going in the opposite direction from this. We're going to have this to t, and then it's going to equal the mass of A times velocity of A2, which is what we want to try to get. That's our first goal as part of this. So remember that these are in US units, so we have to get the mass. We need to divide by 32.2, and we were given a velocity of 13, starting out with feet per second. Then we're going to have our 22 right there. The delta t was given to us of 0.896 seconds. The angle is 15 degrees. We have a friction of 8.5, and the delta t right there is still 0.896. Can be equal to our 32.2, and now here's our VA2. So I do believe that I have to get this. I think it's sometimes good to get the in-between values here. 22 and 32.2 divided 0.683. Whoop. I think I need to multiply by 13. Yeah, I do. So times 13. So we get 8.882. And by the way, the units of these are pound seconds. This is a driver, right? This weight is sending it down, is increasing. This is an impulse that wants to increase the momentum. So that's 22 times 0.896 times sine of 15. So that we could see that it's a 5.102. And that 2 is pound seconds. This part right here, 8.5 at 0.896 is going to get me the 7.616. Okay, notably, this is larger than this, so it will be decreasing right here. So we want to subtract that, and we want to add that. Okay, so we get over on the side here, we have 6.367, but now we're going to divide through by 22, divide by 32.2, divide, and then divide, and I get a velocity of A2 is going to be equal to 9.320 Newton seconds. Pound seconds. Nope. Feet per second. Okay. So now we want to go to page 4. So this was page 3. I labeled it wrong. All right. So page 4. And we'll try to remember to do this. All right. So that's what it is just as it's getting to that collision, right? And I'll show it later, but my preliminary work as I was working through the thing just to see how this would turn out, it originally started like it was going to be 10 feet apart, and so that's actually the time that you would get when they're 10 feet apart. Let me start here. I wanted to go to a meeting here soon. So, but anyway, maybe I want to pause the video and then go to that meeting and then come back. I didn't grade a bunch of stuff in ME470 today too. I just don't have enough time. I didn't do enough stuff on the weekend, but I worked a lot on the weekend. But still, just don't have enough time. I'm asking too much. But anyway, okay. So the next thing that we have to do, we almost have to do the whole thing like over. With a FBD and an IBD, but it'll be quick. But these two things are going to hit each other, right? So that's the thing that we're going to find. They're going to hit each other, and now we want to try to figure out what the friction is going to be. We could take a shortcut, but let's not take a shortcut. Even though I want to be done with this, I might pause the video and come back. I want to go see the robot guy down at the Hersey Center, because I never participate in anything anymore, and I wanted to participate. So maybe I'll do that. But we're going to get the total normal force that's acting onto this, because remember, they're particles. So this is going to be the normal force. I'm going to call it AB because they're both together. And now there's going to be a total friction that's happening onto the here. So FAB. And then there's going to be a weight that's acting on here. There's the weight of A plus the weight of B acting downward. And it's still at that theta going on here. I meant to make that prime and that prime. And then we could find out if we wanted to. Here's the mass of A plus the mass of B. And we call this the acceleration of AB, right? So they're accelerating together. So the sum of the forces in the y prime is mass times acceleration of y prime. Goes to 0. So FNAB minus WA plus WB times the cosine of theta equals 0. FNAB is simply going to be, I wrote this out already. FNAB. Where'd you go, baby? I think it's going to be, it's 22 plus 13, so that's 35, right? Times the cosine of 15. And you're going to end up with 33.81 pounds. Oops. I guess the video went past 15 minutes. That's the 15-minute warning on that, I guess. Okay. And so now we're going to take the friction of AB. It's going to be the kinetic coefficient of friction times the normal of AB. So that's going to be 0.4 times 33.81. And that ends up equaling 13.52 pounds. And yes, I know what you're saying is that you could have totally done that before, but I mean, just without having done all this. Tell you the truth, you could have, but you always run the risk of getting the thing wrong. Now we do the impulse and momentum. And we do initial. We do impulse. And then go final. And let's see, the initial, right? So we have to, we could say it's just before the collision, right, of these two things. Let me think. trying to think. Yeah. Let me think about this for a minute. I'm going to go to that meeting. Hopefully, it's coming back. Okay, so what I wanted to say here is I kind of skipped a step. I don't like how I drew this arrow. So I think it would be okay if I put a little gap right in here. I think this won't be confusing. All right, so I'm going to put a little gap right in here because the initial momentum is only from this box. Okay, so this is going to be MA VA, which was 2, right? Now we're going to go from steps 2 to 3. So right here, I'm going to start to introduce an impact type of idea. There's an equal and opposite force, but there's 2 particles. So it's internal to them, and they're equal and opposite, so they cancel out. And we learned about that actually in the next class. But we could probably put them in there. I'm going to put in the integral of, I'm going to call it P dt. So P dt. And so they're equal and opposite, and of course we still have this coordinate system that we're dealing with. So there's the x prime and the y prime coming down right there. Now I'm going to put in a global normal force. I'll call it FNAB because it's both of them, right? So it is touching right in there. I just drew the arrow kind of far away. And I'll put in a global friction force, which is AB. Whoops, I'm sorry. I need a delta T in there because this is an impulse diagram. It's not a force diagram, it's an impulse diagram. And we also have a weight. Then this is the total weight of the thing, just like we had up here, right? So that's going to be WA plus WB delta T. And it's kind of happening sort of like, I didn't put it, I put it kind of looks like it's the center there. It's really sort of the center of both. Remember, they're particles, right? So the shape doesn't matter. And so what we have at the end right here is going to be MA plus MB times VAB3, I guess. But that better be 0, right? So that's what we're actually asking right here, right? So the time to stop, right? So we had, this is state 1. When it got here, it was state 2. They hit and they move down, and they're going to stop at state 3. So, there's 0 because they end right there. So that's like the big idea. So what we're still saying, L2 is going to be plus imp 2 to 3 is going to be equal to L4, or the summation of momentums at 2, right there, as a velocity, plus the integral F dt. This is time 2 to time 3. It's going to be equal to the summation of momentum. Did I say moments? I think I said moment on accident. Momentum. So what we have here is MAVA2, right? And we need to go say this is in the x prime direction. Yes. Then plus, let's go, I guess it's going to be plus WA plus WB times delta T, and this is T2, 3 delta T, right? 223 delta t maybe. Minus, once again, FFAB times delta t 2 to 3. And that's going to be equal to 0 because it's going to stop. There's going to be no momentum left. So now we can figure out how much time that would take. So we have the momentum from previously. So it's just 22 divided by 32.2 times what we found before of 9.320. So that's the momentum in the x prime direction. Plus our, this 22 and 13, so it's 35 times our delta t 2 to 3, right? And that's going to be, oh, we have to, darn, sorry. This is only the sine of this, right? So we have to go to the sine of theta, and then the minus FFAB delta t 2 to 3, and then that's going to equal 0. Okay, so that goes the sine of, and then we said 15 degrees, right? Yeah. One of the reasons why it works is that it is a very shallow slope compared to the friction. There's large friction of 0.4 and a short slope, so that really helps it. Minus the friction force of 13.52, and that should just be times delta t23 to equal 0. So let's see what that happens there. We have 22, 32.2 divided. We have 9.320 times, right? So this amount right here is going to be 6.368, right? And we might look back at what we had before. Yeah, that's actually what all of this was, which kind of makes sense because that's what that was. And yeah, now I could just subtract that from that. Hopefully it's a negative number, and then I can divide whatever that is over there, and this by whatever that is. Okay, so I get 35 and the sine of 15, so times. All right, and then I'm just going to subtract out 13.52 from that. Yes, it is negative, and then I'm going to divide this other one. Boom. So I say that my delta t 2 to 3 is going to be equal to 1.427 seconds. And I think that's all I really wanted for the answer, so I'll rewrite it out. Answer. There's only one of them. Okay, so delta t 2 to 3 is going to be equal to 1.43 seconds. Now, okay, so this is the end of the problem, but I think there's some insight to be had into what we did here. So let me kind of review this and then show you the alternate things that we could have done. All right, so we knew what the time was between there, but like as a practical thing, maybe you're taking a video of it. Maybe you could scale off the video and you could figure out what the distance was when it was at that point. And notably, I had a very specific amount of time that it was taking before it hit to right there. And while that was going on, it was decelerating that whole time, right? The original problem that I had started here, let's see, do I have a good picture of it? No, I don't really have a picture of it. I had it as 10 feet apart, and I wanted to change, and looking at that, I could do it two different ways when I knew the distance instead of the time. In fact, okay, so I could use Newton's second law, so I'll show that one first. All right, so for Newton's second law, for this first box, I could, okay, here's the impulse and momentum thing I was doing, but here's Newton's second law. So I got the same answer in the y prime direction. Someone's calling me. But here in the x prime direction, I'm able to get what the acceleration is. All right, so if I know the acceleration right here, I can find what the time is going to be, right? Because I have which I could just as easily have written y0 plus v o y plus 1/2 acceleration y direction times time squared. Whoop, supposed to be a time right in there, right? That's the t squared, the time squared one with 1/2 acceleration time squared, right? So I just do the same thing here, and I could find what the time is by taking the quadratic equation, and I get actually two different times, and I got to decide. I picked the lower one, but I also could check that because I could also, with my final velocity, right? I could find the final velocity, let me say it that way, because I know the distance. The distance is 10. I know the acceleration. It was originally 13. I could find what the final velocity was going to be, which is 9.32, by the way. That's the same thing that I got right here by using impulse and momentum. But all I did here was I found the acceleration from Newton's second law. Then I applied constant acceleration kinematics. And well, I got the time here from constant acceleration kinematics, but I could also find what the velocity was from constant acceleration kinematics. And with that velocity, I could also find, now I could find the time. So actually, I confirmed that what I got from doing this one step, I got the time. I could do it from two steps, right? I could get from my knowing the acceleration and knowing the distance, I'm able to get what the velocity is after that distance. And then with that velocity, I'm able to get what the time is, right? Because I have the final velocity, the initial velocity, the acceleration, deceleration, and time. So you just divide out, right? So I was able to get that. Another method, if I know the distance, right, which I did. I knew the distance, and that was able to get me the time, right, by way of Newton's second law. But now I can go ahead and use work energy if I have the distance. So if I have that what that distance is going to be right here, or maybe no, let me think about this. No, this is correct, right? So if I have this distance, I can get what that, with that 10 right there, and there's also the 10 right there, I can get what the potential energy is, that change. Starting with the kinetic energy, I get the potential energy with the change in vertical position right there. And I can also get what the friction energy is going to be. And then I could search for what the final kinetic energy is, which is going to give me the velocity. And with that, I get that other velocity, right? So I get that same velocity here as I got from right there. But I got it like quicker. I didn't need to know anything about the time. And then I could also figure out, once I have this right, with that, if I want to find the distance that they would go when they're together, right? And so that distance I said was going to be 6.65 feet. Now I could actually check that, all right? So I at the final part of this problem here, I say it's 1.43 seconds. And I should probably figure out what the acceleration, deceleration is going to be and compare those two. And I think I'll have the right answer. If I know the deceleration, I'd be able to find that. So anyway, I went way longer than I meant to, but this is an interesting problem because you could do it. Well, you can't actually do it. You could do it using Newton's second law. You could do it using Newton's second law and impulse momentum, but I don't think if I only gave you the time that you'd be able to use work energy. So hopefully that made some amount of sense. If not, you could go back and listen to it again and like pick it apart. And you can see that like we can use any of the three kinetic methods to find the solution in many situations. And some of them, they really lend themselves to one or the other. When it comes to impulse momentum, they really, if we know something about the time, or maybe it's the time we're trying to find, we have all the other information. That's really works well with impulse momentum. If we know the distance something has moved, that really works well with work and energy. So That was kind of my point. 35 minutes.